Hello, everyone. So in this video, we're going to be covering topics from the course of Chemistry 1412, also known as General Chemistry 2. So I'm going to go ahead and share my screen so that you can see a PowerPoint presentation that has been put together. So in this video, we're going to be covering the concept of Clausius-Clapeyron and phase change diagrams. The Clausius-Clapeyron equation shows the relationship between vapor pressure and temperature. So there are two different equations that you can use. The first being ln P equals negative delta H vape divided by R times 1 over T plus C, and the second being ln of P2 divided by P1 equals negative delta H vape divided by R times 1 over T2 plus 1 over T1. So the main thing that you notice about the two different equations is that the second one is going to have two pressures and two temperatures. And in this actual course, the second equation is going to be the one that you're going to be using. So now that we see the equation, we're going to go ahead and define the terms. So the P for the P1 and P2 are going to be representing vapor pressure. And in most of your problems, you're going to see these in either ATM or torr. The second term is going to be T, which represents temperature, and that's going to be represented in Kelvin. So if you're given it in Celsius, you will have to convert to the proper unit. The R variable that is under the delta H vape in the equation is a constant, and it is going to be 8.314 joules per mole Kelvin, and this number will remain constant, hence the name, in every problem that you work. The last variable is going to be your delta H vape, which is heat of vaporization. The delta H vape will be given in kilojoules per mole. However, it must be converted to joules per mole to be used in the equation. This is a step that many students will forget, and they will get the wrong answer on their exams or their homework. So it is very important that you pay attention to the units and are plugging them in properly. So like I said, things to remember. So the first thing I have listed is the actual equation. The first thing to remember is to not forget about the negative sign. That is right here. Do not forget about this negative sign, and to pay attention to your units. So a lot of times you'll have what they call sneaky professors, and they will list every answer choice that you could get on your exam. So they'll put in an answer choice where you did not use the negative. That'll be an answer choice. They'll also do it to where if you did not properly convert your delta H from kilojoules to joules and you solved, they'll put that answer choice as well. So you really have to make sure you're paying attention and doing each step carefully. So before we get into an example of how to do a Clausius-Clapeyron problem, we're going to go through a little review from Chem 1 about conversions. So in this type of problem, there's really just three conversions that you'll have to do. The first is going to be temperature. So in some instances, they will give you your temperature in Celsius. However, like we said, your temperature needs to be in Kelvin whenever you're plugging it into the actual equation. So to convert from Celsius to Kelvin, you simply add 273.15. So I have an example right down here. So if we were given 15 degrees Celsius and we wanted it in Kelvin, we just say 15 plus 273.15, and we'll get 288.15 Kelvin. This should be pretty simple. It is going to be a review from Gen Chem 1. Another one, just to kind of remember, is that 760 torr is going to be equal to 1 ATM. And the third is going to be the conversion between kilojoules and joules. So 1 kilojoule is going to be equal to 1 times 10 to the third joules. So we have an example calculation. If I have 25.4 kilojoules, how many joules do I have? So I kind of set it up on a reaction table. If you just move the decimal, that is completely your choice, but I'm going to show how to do it mathematically. So 25.4 kilojoules is what we're given, so we put that over 1, and because our kilojoules are up on top, we're going to have kilojoules on bottom. So we put the 1 kilojoule down at the bottom, and what we're converting to up here on top, so 1 times 10 to the third joules, and all we do is we multiply by whatever is on top, and we divide by what is on bottom. So because our kilojoules are across each other, we can cancel them out, which means our unit will be now in joules, and you do 25.4 times 1 times 10 to the third, and you'll get 25,400 joules. All right, so our first example for our Clausius clayperon. It says the vapor pressure of 1 butane is 1.268 atm at 273.15 Kelvin, and its heat of vaporization is 22.9 kilojoules per mole. What is the normal boiling point of 1 butane? And sometimes your professors will provide a hint as seen in this problem. It says, hint, what is the definition of normal boiling point? So that is going to be, whenever you see a hint, that is going to be your first clue. Okay, let me focus on that specific topic first before I start solving. So normal boiling point is the temperature at which liquid boils at either 760 torr or 1 atm. So we'll go to our problem, and we're like, okay, our pressure is in atm. So in my problem, I will be using 1.268 atm as one pressure and 1 atm as my other pressure. So I'm going to switch over to a boogie board, and we will actually begin to work through this problem. All right. So the first thing that I highly suggest that you do when you're working through a mathematical problem like this is to write everything out step by step. So the first thing that we're going to do is actually put our numbers with our variables. So we have P1, P2, T1, T2, R, and delta H. You can write it as delta H vape at the bottom, or you can just put it as delta H. So when we're looking at our problem, we know that our first pressure, which was provided in the actual question, was 1.268 atm. And the hint that they gave us told us that our second pressure was going to be 1 atm. Our temperature, the temperature that was provided was 273.15 Kelvin. The question asked for the second temperature. Our R value is going to be our constant number, so 8.314 joules per mole Kelvin. And then our delta H was 22.9 kilojoules per mole. However, like we said before, we cannot plug it in to our equation in kilojoules, and we know that because our R value says that it has to be in joules. So before we even plug anything in, we want to go ahead and convert our delta H from kilojoules to joules per mole. So I'll set it up just like we did before on a reaction table. All right, so because we have kilojoules up on top, we have to put it down here on bottom. So 1 kilojoule was equal to 1 times 10 to the third joules. And so we'll multiply everything that's on top, divide by what's on bottom, which is just 1, and we will get 22,900 joules, which means our delta H is going to be 22,900 joules per mole. And we'll be able to put each of these variables into our actual equation. So I'm going to go ahead and erase the board so I can plug them all in. So I always start by writing the equation out plain before I start to plug it in. So we had ln of P2 divided by P1 equals negative delta H divided by R times 1 over T2 minus 1 over T1. So this was the blank equation, and now I'm going to put all the numbers that we had before in. So we have ln of 1 ATM divided by 1.268 ATM equals negative 22,900 joules per mole divided by 8.314 joules per mole Kelvin times 1 over x, because we don't know this variable, minus 1 divided by 273.15 Kelvin. All right. And so what I like to do is to cancel out the units so I know what my final answer will be in. So our ATM can cancel out, our joules per mole can cancel out, and because our kelvins are both on bottom, our Kelvin can't cancel out, which means our answer will be in Kelvin. So I do this because it's easier when I'm writing through each step to not have to put all of the variables. However, if it makes you more comfortable, you can keep writing the variables throughout the process. So the first thing that I'm going to do now that I have my variables canceled out is begin to solve through the math and then solve for our x variable using algebra. So when you plug in ln of 1 divided by 1.268, you're going to get negative 0.237. And I'm going to put that equal. And then I went ahead and divided my 22,900 divided by the 8.314, keeping in mind that it's negative. And you will get negative 2,754.39. And then I'm just going to bring my temperatures down. Okay. And then slowly we're going to want to move everything over to get that x by itself. So because our negative 2,754.39 are being multiplied by our temperatures, we're able to divide to get this value to the other side. So we're going to say negative 0.237 divided by negative 2,754.39 equals 1 divided by x minus 1 divided by 273.15. And because both of these are negative, it's going to become a positive value, and it's going to give us 8.604 equals 1 divided by x minus 1 divided by 273.15. I can now add this section to be able to get it over on this side. So we're going to have 8.6104 plus 1 divided by 273.15 equals 1 divided by x. And we're going to have 0.0037 equals 1 divided by x. And then if you move the x over, so it becomes 0.0037 x equals 1, and then divide by the 0.0037, so you're going to have x equals 1 divided by 0.0037, so our x is going to be equal to 266.9 Kelvin. We know it's in Kelvin because that is what we said our final unit would be in. And that is the end to this problem. Okay, so I'm going to go ahead and erase it, and we're going to go back to our PowerPoint. All right, now a second example. It said liquid sodium can be used as a heat transfer fluid. Its vapor pressure is 40 torr at 633 degrees Celsius and 40 torr at 823 degrees Celsius. Calculate its heat of vaporization. So remember, heat of vaporization is going to be that delta H vape. I'm going to exit this and go back to the boogie board, and we're going to do the exact same steps that we did before. So the first thing we want to do is define our variables. So we have P1, P2, T1, T2, R, and delta H. So our pressure 1 was that 40 torr. P2 was 400 torr. T1 was 633 degrees Celsius. T2 was 823 degrees Celsius. R was 8.314 joules per mole Kelvin. And delta H is our X value because we don't know what it is yet. However, before we get started, we have to look back at our temperatures. So to plug it into the equation, we cannot have it in Celsius. We have to have it in Kelvin. So we add 273.15 to both of them to get our temperatures into Kelvin. So we're going to get 906.15 Kelvin for temperature 1 and 1096.15 Kelvin for temperature 2. All right, so I'm going to go ahead and erase this, and then we will begin to plug it into our equation. Just like before, we want to first write our equation out without the numbers in it. So we have ln of P2 divided by P1 equals negative delta H divided by R times 1 over T2 minus 1 over T1. All right, and then now that we have the blank one, we can begin to plug it in with our numbers. So we say ln of 400 torr divided by 40 torr equals negative delta H, because we don't know what it is, divided by 8.314 joules per mole Kelvin times 1 over 1096.15 Kelvin minus 1 over 906.15 Kelvin. So we know that our torrs will cancel out, and so far that's the only thing that we can cancel out just right now. So I'm going to go ahead and take the ln of 400 divided by 40 and plug it in. When you plug this into the calculator, you'll get 2.30 equals negative delta H of 8.314 joules per mole times Kelvin, and then I'm going to go ahead and plug in my temperatures. So when you plug that into the calculator, you'll get negative 1.913 times 10 to the negative 4 Kelvin. And this is kind of written the same way as putting a 1 underneath, which means our Kelvin can now cancel out. So we're left with joules per mole, which makes sense because that is what delta H will be plugged into for this equation. So we'll put joules per mole is what we will get out of our answer. So now all we have to do is solve for our delta H. So using algebra, I start to move everything over. So I say 2.3 times the 8.314 equals negative delta H times negative 1.913 times 10 to the negative 4. So when you plug the 2.3 times 8.314, you're going to get 19.1222 equals negative delta H times negative 1.913 times 10 to the negative 4. They are multiplying, so all you have to do is divide our left side of the equation by what our temperatures were calculated to be. So you'll do 19.1222 divided by negative 1.913 times 10 to the negative 4 equals negative delta H. Ensure when you plug it into the calculator that you have this in a parentheses. Otherwise, it could give you the incorrect number. So you're going to get negative 99,959.226 equals negative delta H. They're both negative, so you can cancel out the negative number. And this is saying that delta H is going to be equal to 99,959 joules per mole. However, that's not what your answer choice will be in. It's going to be in kilojoules because that is what delta H needs to be in. So before you circle an answer choice, you have to convert our 99,959 joules per mole into kilojoules per mole. I'm going to go ahead and erase this and begin to set it up on a reaction table. So we have 99,959 joules, and because our joules are on top, our joules will be on bottom here. So we have 1 times 10 to the 3rd joules for every 1 kilojoule. So our joules cancel out. We multiply what's on top, divide by what's on bottom. So you'll end up having 99,959 divided by 1 times 10 to the 3rd. And you will get 99.9 kilojoules, which means our delta H is 99.9 kilojoules per mole. And that is how you solve this problem. All right, let me switch back over to our PowerPoint. For example 3, it says at 34.1 degrees Celsius, the vapor pressure of water is 40.1 torr. What is the vapor pressure at 85.5 degrees Celsius? Your delta H vape of water is going to be 40.7 kilojoules per mole. Switching back over to our boogie board, we will begin to define our terms. So we have P1, P2, P1, P2, R, and delta H. Our P1 was 40.1 torr. Our P2 is what we're looking for, so it is X. P1 is 34.1 degrees Celsius. T2 is 85.5 degrees Celsius. R is 8.314 joules per mole Kelvin. And our delta H is 40.7 kilojoules per mole. So there are two conversions that we will have to do for this problem. The first being temperature. So we know that we cannot have it in Celsius, so we have to convert it to Kelvin. So just like we did in one of the previous problems, we have to add 273.15 to each of these temperatures. So we'll get 307.25 Kelvin and 358.65 Kelvin. The second is our delta H. We have it in kilojoules, however, to plug it into our problem, it has to be in joules. So we'll set it up on our reaction table. So we have our given divided by 1. Because we have kilojoules, our 1 kilojoule is on bottom, while our 1 times 10 to the third joules is on top. The kilojoules will cancel out, and we will get 40,700 joules per mole. And now we have everything in its proper unit to plug it into our equation. So just like we did before, we're going to write out our blank equation. So we have ln of P2 divided by P1 equals negative delta H divided by R times 1 over T2 minus 1 over T1. So now that we have our blank, we can begin to plug our numbers into this equation. So we have ln of P2 divided by 40.1 torr equals negative 40,700 joules per mole divided by 8.314 joules per mole Kelvin times 1 over 358.65 Kelvin minus 1 over 307 I'm going to write it right down here, 0.25 Kelvin. All right. So automatically we know our joules per mole can be canceled out, and so far nothing else can be. So the only thing that we can kind of work right now is going to be the things on the right side of the equation. So we'll rewrite the left side. So ln of P2 divided by 40.1 torr equals, when you plug in negative 40,700 divided by 8.314, we're going to get negative 4,895.36 Kelvin. And remember, that was on bottom. And then we plug in our temperature, and we get negative 4.66 times 10 to the negative 4 Kelvin. Our kelvins now cancel out, and we're going to be left with torr, which means torr is the unit that our final answer will be in. Everything that is on the right side can now be multiplied. Because we have two negatives, it's going to become positive. So you have ln of P2 divided by 40.1 equals, and this is going to be 2.28. And that's with these two numbers right here multiplied by each other. And now we just have to work to be able to get our P2 by itself. So the first thing we have to take away is this ln. When you bring it to the other side, it's going to become e to what is raised on the right side. So we have P2 divided by 40.1 equals e to the 2.28. This will become P2 divided by 40.1 equals 9.78. It's dividing, so you will multiply. So you have 40.1 times 9.78 equals P2. And so your P2 will be equal to 392 torr. And that is how you solve the third example. All right. So that is the last example for Clausius clapeyron. Before we move into the phase change diagrams, we have to be able to understand some terms that you'll see in the problem. So this is a chart that kind of explains what is happening and the names for them for phase changes. So there are three phase changes, the first solid, then liquid, and gas. When you're going from solid to liquid, it's going to be melting. From liquid to gas, it's vaporizing. And if you work backwards, so if you're going from gas to liquid, it's condensing, just like we see on the outside of a glass that has ice in it on a hot day. And then when you're going from liquid to solid, it's going to be freezing. That's like putting water in the freezer and it becomes ice. When you're going from solid all the way to gas, it's going to be called sublimation. And when you're going from gas straight to a solid, it's going to be deposition. So the top section is all going to be endothermic reactions. So this is going to be a term that you heard back in Gen Chem 1. So endothermic means that the heat is being put into the system, which makes sense because if you put heat into a system, it can sublimate all the way to a gas. The bottom section of this diagram is going to be exothermic reactions, which means heat is being released, which makes sense. So if you're thinking of water, you have to release heat for it to freeze to become solid. So these are some terms that you'll have to know for some of the examples that we will do with phase change diagrams. A practice problem, just to make sure that you got a hang of it, it says the change of a material going from solid phase to gas is called blank and is a blank process. This is going to be sublimation, and it's an endothermic process. And this is done just by looking at this diagram and remembering it over time. So here is an example of a basic phase diagram. So you're going to see pressure on the y-axis, and you're going to see temperature on the x-axis. Try to ignore the dotted lines just for now. There's a line right here. It hits this middle point, and it breaks off into two lines, this first one being the green, and the second being the blue. This will break it up into three different phases. So this whole section right here is going to be your solid phase. This middle section is liquid phase, and this bottom section is a gas phase. You will have to remember this because it's not always written out on the exam. You'll notice that there are two red dots. The first one is labeled triple point, and the second one is critical point. So your triple point is where all three phases, all solid, liquid, and gas phases, are in equilibrium. And this dot right up here, which is critical point, is where the densities of liquid and gas are equal. So you're going to hit both critical pressure and a critical temperature. So when you're doing problems like this, the way that you kind of read it is, say I have a line that is going from the gas phase up into a straight line into the solid phase. So I just have a straight line going up and down. And if they wanted you to explain what was happening, so you would say that it's going from gas phase to solid phase at a constant pressure, at a constant temperature and an increasing pressure. So it's a constant temperature because it's straight up and down, and it's an increasing pressure because it's pointing upwards. Now let's say that we had a horizontal line. So we have a line going this way. So this would be an increasing temperature, a constant pressure, going from solid to gas phase. So that's kind of how you're reading it. And it's a pretty simple concept. It's probably the easiest concept that you're going to have throughout this entire semester. So now we're going to go through a couple examples. So this could be the example that they give you on an exam. So which of the following shows the sublimation of a compound? And you're given this diagram. So ignore the 1, 2, 3, but you're looking at the letters in the line. So you have to remember, 1 is your solid, 2 is your liquid, 3 is your gas. Do keep in mind that not every single phase diagram will look exactly the same. So you'll notice in this one, it curves more to the right, but in this one, it's kind of broken up into kind of even, but the gas is normally pretty big. Each element or compound will have its own diagram, but it's still going to be set up the same way. So you're always going to have your solid, always liquid, always gas, and you'll always have your triple point and your critical point. So the first part of this problem, we have to determine what is sublimation. So if you look down here, sublimation is the process from solid all the way to gas. So you're not hitting that liquid phase. So you have to look and see which one is moving us from solid to liquid. So if we're looking at A, we know that this one is connecting solid and liquid. Sorry, we're going solid gas. B is going from liquid to gas, or vice versa. Same thing with C. Also remember, B is your critical point. D is your triple point. So we're left with E. So we have solid here, and it's connected to the gas phase. And so E is the only answer that would make sense. Example 2. So this one looks slightly different. So this is similar to what I was talking about. So if they give you a line and they want to know what's happening between these 2 points, so you have a bunch of different ones, they want to know which one represents condensation. So remember, condensation is the movement from gas to liquid. So we know that we're going to have to deal with one of these two. So it's either going to be from G to H or from E to F. The main difference is one is pointing up and the other is pointing down. So because we know that condensation is from gas to liquid, we start at the gas. So the one that is pointing from gas to liquid phase is going to be our G to our H. So that would be our answer choice for this problem. That's pretty much all there is when it comes to phase diagrams. So let me go ahead and give a brief overview of everything that we covered in this video. So the first concept we covered was Clausius-Clapeyron. The equation that we will use for this course is going to be the ln of P2 divided by P1 equals negative delta H vape divided by R times 1 over T2 minus 1 over T1. Reminder to pay attention to the units and not to forget the negative sign. This is going to be what kills everyone when it comes to the exam. You have to make sure that you're paying attention to your units and that you do not forget that negative sign. Otherwise, you're going to pick the wrong answer. I highly suggest to take these problems step by step, double check what you solved for, and that it is in the correct units. So just like in our last problem with the Clausius-Clapeyron, we solved for our delta H, and it was in joules per mole. However, our answer has to be in kilojoules, so you have to do one last conversion to be able to get your answer correctly. For the phase diagrams, remember the general diagram and where everything goes. So remember where the solid, liquid, and gas sections on the phase diagram are. Know where the triple point is and the critical point. Know what they are, and then also know the terms for moving from one phase to the other. Also, carefully read through each answer choice and pick the answer that best fits the diagram. So generally, there's not going to be more than one answer that will fit the diagram. Sometimes they can be worded like in a tricky format. For those, all you have to simply do is raise your hand during an exam and see if the professor will allow for an explanation of what that meant. Most of the time they will, but each professor is slightly different. So let me go ahead and end my sharing. That is going to be all that we have for today. Thank you and have a good day.